Have you ever stopped to think about why a sidewalk is a certain width? Or why a curb is a specific height? Well, I can tell you it is not random. It's all part of this secret code book for urban planning. And today, we're going to crack that code.
Oh man, we've all been there, right? You're stuck in an endless traffic jam, or maybe you're doing laps around the block just searching for parking, and you're thinking there has to be a better way. It might feel like total chaos, but a lot of it is actually by design. It's a whole system of rules. And today, we are going to decode that system together. So here's our game plan. First up, we're going to untangle those nasty traffic jams. Then we'll crack the code on parking. Where do all the cars go? After that, we'll look at how streets are actually designed for people, not just cars. And to wrap it all up, we'll see how our cities are getting seriously smart.
Okay, our first stop is the intersection. You know, it's the heart of the city grid. But let's be honest, it's often the source of our biggest headaches. But believe it or not, there's a real science to making them actually work.
So the entire science of intersection design, it really boils down to this one idea: conflict points. Just think of it as any spot where things could go wrong. You know, where two cars might try to occupy the same space at the same time. The number one goal for any traffic engineer is to get rid of as many of these points as possible. Now, these conflicts really fall into three main types. You've got merging, which is just two lanes becoming one. You've got diverging, where one lane splits into two. But the big one, the most dangerous one by far, is crossing. That's the one that engineers are obsessed with eliminating, because that's where the really bad accidents happen. So how do you get rid of those dangerous crossing conflicts? Well, for moderate traffic, we're talking up to 3,000 passenger car units per hour, which is just a standard way to measure traffic. A roundabout is perfect. It cleverly turns those risky crossings into much safer merging and diverging moves. But for the really heavy-duty traffic, you've got to bring out the big guns. A grade separator, what most of us just call a flyover. It separates traffic onto different levels, which gets rid of the conflicts entirely. And here it is, the magic number, 10,000. 10,000 passenger car units per hour. According to the Indian Roads Congress Codebook, once traffic hits this level, it officially justifies the massive cost and effort of building a flyover. It's not just a gut feeling, it's a decision driven by pure data. All right, let's switch gears. We've gone from moving cars to, well, storing them. It's time to crack the parking code. Because we all know that after every single drive, there's the epic hunt for that elusive spot. Okay, now this is a really big shift in thinking. Planners don't just see parking as a place to leave your car anymore. The official guidelines actually call it a demand management tool. What that really means is that the amount of parking they build is used strategically to control how much traffic flows into an area in the first place. Kind of clever, right? So how much parking does a building actually need? Well, it's all written down in the code. Developers have to provide a certain number of spots, and they measure this in something called equivalent car space, or ECS. So for every 100 square meters of space, a commercial building needs 3 spots, while a fancy residential one needs 2. And when you're designing that parking, it's all about trade-offs. The 90-degree perpendicular parking, you know, the kind you see in most big lots, it fits the most cars, high capacity. But it also needs a really wide aisle for cars to get in and out. Then you have parallel parking, which is the least efficient for space, so you mostly just see it on streets for quick stops. It's this constant puzzle of maximizing every square inch. All right, we've talked a ton about cars, but what about us, the people actually walking through the city? Let's shift our focus to the rules that are designed to keep us pedestrians safe and, you know, comfortable. This number, 1.8 meters, might seem totally random, but it's actually incredibly human-centric. This is the minimum standard width for a footpath. And why? It's simple. That's the amount of space needed for 2 people to walk next to each other and have a conversation without one of them having to drop back. It's a rule that's literally based on social comfort. Here's another one of those little numbers that secretly shapes your daily walk: 150 millimeters. That's about 6 inches. This is the standardized height for a city curb, and there's a really clever, dual-purpose reason for this very exact measurement. See, this 150 millimeter height is the perfect sweet spot. It's just high enough to act as a barrier to stop cars from accidentally driving up onto the sidewalk, but it's also just low enough to line up perfectly with the floors of modern low-floor city buses, making them accessible for everyone. It's one simple number that's solving for both safety and inclusion. Pretty cool.
Okay, in our final section, we're looking to the future. We're going to see how technology is being layered right on top of all this physical infrastructure. So, welcome to the world of intelligent transportation systems, or ITSs for short. So, how exactly does a city get smart? Well, on the left, you've got adaptive signals. These aren't your old school traffic lights on a fixed timer. Nope. They use AI and live camera feeds to react to traffic as it's happening. And on the right, you have variable message signs. You've seen these, the big digital boards that give you live travel times or tell you if a parking garage is full. So one manages the flow of traffic, and the other manages information for the driver.
Okay, we have decoded a lot of the city's secret rules. So now, I think it's time for a quick pop quiz to see what's stuck. You ready?
First question for you. At what traffic volume does that huge infrastructure project, the flyover, get the official green light?
And the answer is C, 10,000 passenger car units per hour. Once traffic hits that critical point, the codebook says it's time to build up and over to keep the city from grinding to a halt.
Question 2 is all about parking. Which layout lets you cram in the most cars, but there's a catch?
That's right, it's C again, 90-degree perpendicular parking. It gives you the absolute highest capacity, but it comes at the cost of needing that big, wide aisle for cars to get in and out. And for our final question, what is that magic number for the height of a curb that strikes that perfect balance between safety and accessibility? The answer is B, 150 millimeters. It's that perfect Goldilocks height, tall enough to stop a car, but low enough for an accessible bus. Just a simple but brilliant piece of urban design. So the next time you're walking or driving around your city, I bet you'll see it a little differently. You'll start spotting the conflict points, you'll notice the height of the curb, and you'll understand the logic behind that parking lot. These aren't just random features. They're all part of a code. And now that you know how to read it, the real question is, what would you change?